Okay, folks, let's talk about the unit circle here in relation to what we've already learned in the course. So, um, section 7.1 is all about the unit circle, and this is a diagram from that section in the book, but I'm going to change it and say, let's review what we already know. So instead of saying that this is a circle of radius 1 or a unit circle, let's call this a circle of radius r, so that the equation of this would be x squared plus y squared equals r squared. And we can call this a non-unit circle. All right, now keep in mind that we've talked about how if we examine an angle in standard position, so that means the vertex of the angle is at the origin, and I'm going to rotate counterclockwise would be in a positive direction. We can call the angle theta with respect to the positive x-axis and this terminal side of the angle. And we said if we can identify one point on the terminal side of that angle, so we'll call that point x and y, or point xy, I guess, that we can establish the 6 trig ratios from this point and the radius of the circle, or the distance from the origin, are here and that point. All right, so keep in mind that r squared is just x squared plus y squared. All right, you can call that Pythagorean theorem if you want to draw a little triangle, or just apply the equation of a circle here. Same difference. All right, and we've already established that we know that the sine of my angle theta will be y over r. The cosine of theta will be x over r, and the tangent of theta will be y over x. And then we also have the reciprocal ratios, which are the cosecant of theta is r over y, the secant of theta is the reciprocal of cosine, r over x, and then the cotangent is the reciprocal of tangent, so x over y. So we can express the trig ratios in terms of the angle theta and this distance r and the coordinates x and y. All right, now we use this fact along with a couple of other facts to write these ratios for just about a couple of other facts, I should say, to write these ratios for just about any angle theta. So we said, all right, we can talk about, here's a coordinate plane here, my x and y axis. I can talk about an angle theta in the fourth quadrant. So remember, if I define this guy to be theta right here, then my reference angle, right, is right here with respect to the positive x-axis. And I know that, again, if I identify a point on the terminal side of my angle, call it xy, I know that, for example, the sine of angle theta is going to be the negative of the sine of the reference angle. All right, so it's still going to be y over r, again, where r is the distance from the origin to the point. But I know that I can use a little right triangle here, a reference triangle, along with this reference angle, and figure out the sine of the reference angle, and I know it's going to be the negative of the sine of theta because I know that sine is negative down here in this fourth quadrant. Why? Because the y value is negative. So we've already done problems such as this, where we've determined the values of the trig ratios for angles in various quadrants, the fourth quadrant, the third quadrant, and so on, through using a little reference triangle and a reference angle. All right. So we used that information. We also used information such as special right triangles, and we said, well, what if you have a 30, 60, 90 right triangle? And I said, well, here's a handy 30, 60, 90 right triangle with a hypotenuse of 2, a short leg of 1, and a long leg of root 3. We use these numbers as well as to find exact values. And then we also used another special right triangle, the 45, 45, 90 right triangle, and said, all right, well, what if your legs are 1? Well, then your hypotenuse is root 2. So again, we use these values to determine exact values for the trig relationships. So these are things we've done so far in the course. And the only difference between this and what we call the unit circle is that now instead of saying my circle is of radius r, we force the radius to be 1. And so if I identify a point xy on the unit circle, again, here's my distance r is 1. I know that if this angle's theta, then the sine of theta is still going to be y over r, but since I'm forcing r to be 1, that's y over 1, so I know that the sine of theta is just y. And then similarly, I can say the cosine of theta is x. So anywhere on this unit circle, if I look at the angle formed by the origin and the terminal point, the origin and a point on this terminal side on the unit circle, I know that the x-coordinate will give me the cosine of the angle theta, and the y-coordinate will give me the sine. And then similarly, y over x is going to give me the tangent. Okay. So all I'm doing in this section is scaling this down and forcing r to be 1. Everything else is exactly the same as what we've studied so far. If I look at my my special right triangles, if r is forced to be 1, that would mean I'd have to force the hypotenuse of these two triangles to be 1. Well, I can do that by just scaling down the triangle. And instead of 2, I'm going to say, well, let's make this hypotenuse 2 over 2, which is 1. And I'm going to similarly divide the two legs by 2. So if I'm going to talk about the unit circle and x and y being the sine and the cosine of these values, I perhaps now can use a scaled down version of this 30, 60, this isn't drawn to scale, 90 triangle where my hypotenuse is 1, my short leg is 1/2, and my long leg is root 3 over 2. Okay, I can do a similar thing here with my 45, 45, 90 right triangle and say, well, let's just divide by root 2. So I've now forced my hypotenuse to be 1, root 2 over root 2, and my legs are now, so these are 45, so they're equal. My legs are now 1 over root 2. Okay, so everything we've learned in the previous sections applies to section 7.1, except that now we're forcing the hypotenuse of our reference triangle, I guess, or the value r in terms of the point xy to be 1.